Now, can you start it? And you need to explain the idea first, and then you can code it up. Finally, you need to tell me the time complexity and the space complexity, and you can start now.
Today we're going to solve a hard sliding window problem called sliding window maximum. So we're giving obviously an input array and a sliding window of size k, which moves from the left to the right of the array. And you can see a maximum of k frequency of numbers, k in terms of length in the window. And each time the window obviously moves right by one position, so we want to return the maximum sliding window, which essentially says for k elements, the biggest one should be 3. For k elements, the biggest one should be 3, and vice versa until we get to the end. So the first question to ask is how many windows are we going to have in this, right? So we know k is a size 3, and we know the length of the array is of size 8. So we're going to have length of nums divided by k, number of windows. Oh, sorry, length of nums minus k, number of windows. So we're going to have 5 windows. 1, 2, 3, 4, 5.
6.
And the way you know that you've reached the end is because, 3 has reached the end. So yeah, we're going to have 5 different windows.
No, 6.
6 windows, sorry.
Yeah.
Because the last one is inclusive. Yeah. Because the first one and the last one are inclusive. Yeah, so we're going to have 6 different windows because we're talking in terms of indexes and we're looking at the length. So yeah, so the way we're going to solve this problem is using a deck, and we are going to look at our array. So our deck is empty. What we're going to do is we're going to push an element onto our deck. We're going to push the index of the element onto the deck. And then we're going to see, have we reached the Windows limit of size k? No, because k equals to 3. So that means we can still keep adding more elements onto the deck. So we're going to add 0 and 1 to the deck. And so now we have elements to actually compare to, because we have 2 digits to say, is 3 bigger than 1? Yes, because the idea is we are going to keep the maximum digit of each window at the beginning of the deck, and we're going to keep sliding the window. And if we see a number that's bigger than the rear of the deck, then we're going to actually slide this down. So we're going to have 1 and 3. So again, we're talking in terms of indexes, but if we were to do these in terms of the digit, we would 1 here and then 1 and 3. And we're going to keep adding elements, but we haven't reached size k yet. So because we've already seen an element that's bigger than whatever's on the rear of the deck previously, then we can already pop the element off and we can keep sliding our window. So now, because our window is of size k, we know that we can actually calculate what's going to go in the first place of the resulting list. Right now, -1 is not bigger than 3. So we know that 3 is going to be our result because our result is always going to be at the very front of the deck. And so after we've reached size of k, now we can shrink the window. And once we shrink the window, we're not of size k yet, so we can expand the window again. And since we hit -3 now, -3 is not bigger than 3. Whatever's at the rear of the deck is what we're going to compare to. So because of this, again, the beginning of the deck is going to be our result. So index 1 of the result list is still going to be 3, as you can see. And we're going to shrink our window. Again, nothing we're seeing is still bigger than 3. And then we're going to expand the window again, and now we get 5. 5 is bigger than the rear of the deck. So we're going to pop off the deck, and we're going to append to the beginning of the deck this number 5. And now we've reached size k. So every time we reach size k, put the first index of the deck into the corresponding position in the resulting list. which is just going to be the rear of the resulting list. And so we keep doing this until we get to the end. And so the time complexity of this is O of n, because sliding window means we only iterate through the array once. And yeah, so the idea is, again, to keep a deck and to make sure that the maximum value is at the front of deck and the minimum value is at the rear of the deck. Once we slide our window to the right and we find a number that's bigger than the rear of the deck, then we know that already that's not going to be the biggest number in the window, because we keep sliding the window until we reach a size k. So we pop the rear of the deck and then add our current bigger number to the rear of the deck. And so basically the idea is we're going to have our deck and we're going to slide the bigger number to the left, to the left, to the left, as long as we populate the deck, which the deck is going to be, it can be bigger than a size 1. For example, if we're going to add to the deck 1 and 3 here, it might be bigger than 1. But as soon as we reach this, because we know that, we know that -1 is not bigger than 3. So then we can we can slide this down so 3 becomes the first index of the deck. And because 1 is popped off, why is 1 popped off? Because 3 was bigger than 1, so we know we don't even need 1 anymore. So when 1 was popped off the rear, the front of the deck, then 3 automatically slides down. So I hope that makes sense, but I'm going to code it up now. And
okay, you can start code up.
So first of all, we have our result list. And then we have our deck, aka doubly ended Q, and we're actually going to just iterate through our nums array. This guy paves the path to increase the window, and we're going to have a left pointer that's going to be the beginning of the window. So at the beginning, obviously, our deck is empty, so we're not going to do anything. We're going to append the index of the first element. But in the case where the current element is bigger than the rear of the deck, as mentioned, then we're going to pop before appending the index. But I know that this is the value, but it works out because we're going to need the index anyways. So, okay, cool. So now we have one element in our deck. So we're going to make sure that there's nothing where we haven't crossed the boundary where we're of size k yet. So this is not going to be true in the first turn. But in the case that left is bigger than the front of the deck, this means this is how we shrink the window. So we're going to pop left to basically get rid of whatever's at the front of the window. So this is not going to be true in the first iteration. You could ignore that because obviously we're not of size k yet. But in the case that we've reached the size of our window, then we can append the rear element, because again, the deck contains indices. So if we plug in the index here, nums of I, then we can get the actual value. And then we also have to increment left pointer because we've already reached the size of k as our window. So now we have to actually shrink the window. So after we've incremented our left pointer, automatically when we go here, we're incrementing our right pointer. And then when we get here later, we're already seeing that left is bigger than 0, because right now the deck is index 0, right? The first element is always index 0. So 0 is never going to be bigger than 0 in the first turn, right? But in the future iterations, when we've already incremented left and we come back here, and then this becomes what it is, and now we can pop the left element from the deck. Pop left means pop from the front of the deck. And then after we iterate through the entire, slide the window through the entire input list, then we can actually return the result.
Okay, you can
So-
run it.
There's one thing I wanted to discuss as well. I think
Oh, okay. Which one you
just
want
to
to
make sure
discuss?
this is correct. Results appending. This is not correct because we want whatever's on the front of the deck. But we want the number, so it's nums of D0, sorry. Because our deck contains indices, we want the actual value on the resulting list.
Mhm.
Okay, now let's run this.
Ooh,
Oops.
okay.
It's supposed to be right. Sorry. Because we're seeing if our window is at least of size K.
Ooh,
there you go.
Ooh, yeah, nice. Talk about. Can you explain the time complexity?
The time complexity is O of n because we're only iterating through the input list once.
Okay, only one time,
The space
right?
complexity, I think, is O of n now instead of O of 1 because we have this extra deck which uses extra memory. And we have a resulting list as well.
Okay. Okay.
But the appends and the pops from the deck are in constant time, so that doesn't add to the time complexity. But it's still O of n time complexity because this by itself costs O of n.
Yeah. The worst case is B of n squared. Yeah, but it's fine. B of n, yeah, it makes sense. Yeah.